Well, good morning, everyone. So traditionally, the first talk in the morning after the conference dinner is not the prime time. That was particularly true this time. But I'm delighted to be here, and I'm delighted to have an opportunity to talk about Roman. And I'd like to start first by showing a video of our hardware progress, because if a picture is worth 1,000 words, a video is worth 1,000 pictures. So let me just go. So we now have an observatory. The video that I showed ended in November, just after the telescope had arrived. And since that point, we've integrated both instruments into the instrument carrier, which is that kind of grid-like structure. We've integrated the telescope into the instrument carrier. That makes the integrated payload assembly. We've installed all of that on top of the spacecraft. And the spacecraft, along with lots of other stuff, houses the flight electronics for the telescope and the instruments. So this particular unit here allows us to take photons through the telescope all the way to through the instruments controlled by the flight electronics. So this is our main test unit for the next year or so. It's being mechanically integrated. We're currently working on electrical integrations. There's a lot of care before you plug one thing into another thing. The spacecraft itself has about 45 miles of cables inside it, so it's a non-trivial task to integrate this electrically. Once that gets completed in March, we will be beginning EMI, electromagnetic interference testing, And in July, we will begin thermal vac testing of this unit, and that will, really be our final end-to-end test of the system. In parallel with this, those of you who know what Roman is will realize this isn't actually the complete observatory, because we do have an outer bit. We have an outer barrel assembly that goes around the telescope. We've got solar array sun shields that shield us from the sun and provide power. And we've got a deployable aperture cover. And those three items are being integrated together and separately going through their own testing, and it will all come together next year, and we remain on track for an October 2026 launch, which is simultaneously exciting and terrifying. A couple of weeks ago, we had our final gateway review. So we now have permission from the NASA administrator to proceed into phase D. What's important about that is it unlocks the final slug of funding. We remain on time and on schedule and on budget, but it hasn't been complete. I mean, if I said we didn't have any issues, you shouldn't believe me. So we've encountered things and fixed them. We found a light leak associated through the prism and grism and filters on the in the wide field instrument. There was also a stray light path in the coronagraph. All of these were fixed by adding baffles. Spurred by feedback that we got from Euclid, we have been carefully redoing our stray light analysis, and that's uncovered another couple of potential paths that we have added baffles between the wide field instrument and the sort of structure into the telescope. But we're able to accommodate all of those adjustments within the schedule. Okay, so what are we doing this for? If you sort of look at Roman's mission objectives, our first objective is to do astrophysics with wide field infrared surveys. We have, and that's enabled by having a large field of view and a sensitivity that is broadly equivalent to Hubble. So what that means, for example, is you can take a month of Roman data, do a survey of the galactic plane, and have the potential to detect something like half the stars in the galaxy, making immediately a very large astronomical catalog, and that's with just 1 month of Roman data. We have mission objectives in cosmology and exoplanet demographics, and those mission objectives are specific. So we can use those to define the requirements against which we need to build this observatory. So that's what drove how wide our field of view was. It's what drove what choices of filters we have. It drove the need for efficient survey observations. But of course, all of these things help astrophysics too. And then we address astrophysics in how we actually implement and execute the mission, and I'll come to that in a moment. We're a survey mission, and what that means is that every Roman observation will be used by many different groups from many different science areas. So you really want to define as much of our observing program as possible in a collaborative way, because you are not going to get the optimal observation if you set things up in a way that encourages people not to share their ideas. So we have aimed in Roman to really promote collaboration over competition. And we have an extremely large data volume. If you're surveying the sky 1,000 times faster than Hubble, you're going to have 1,000 times the data volume. And that means that we need to be very deliberate on how we plan to process and reprocess. And we need to be very deliberate on the set of high-level science data that we produce, because the community is not going to be able to process data large chunks of data from level 1 by themselves because it's computationally infeasible. We're providing a cloud-based compute environment, so you can do your analysis adjacent to the data. So now that we have an actual observatory, the focus is on how we're actually going to use it. One thing that we need to be careful of is sort of where are we going to look? What are we going to do? The Roman Observing Program has 3 very large surveys that we call core community surveys that are designed to address the cosmology and exoplanet requirements and the wide field infrared survey requirements. And the way that you can think of this is that the exoplanet and cosmology science objectives anchor the surveys, and the optimization considers all of the science output from this. We also have time available for additional surveys of whatever people want to do. So this could be things to extend the core community surveys. It can be entirely new observations. There will not be many of these. There's no more than 30 over the life of the mission. And then finally, we have a coronagraph that will conduct a 90-day set of observations around 3 weeks or so needed to demonstrate their technical requirements, and the remainder to push boundaries either on science or additional technical development demonstration. I'm going to move on from this because I think I'm already running out of time. Okay, so the core community survey, I want to say a brief word about this. So Scott was going to include this in his talk, but he is no longer immediately after me. So I wanted to say a word about what we've been doing. So to get this collaborative definition of our surveys, we set up three committees, one for each survey. We had several rounds of soliciting input from the community. So we had virtual workshops, we had calls for science pitches, we had white paper calls, we had more virtual workshops, we had intermediate periods where each of these committees described where their current thinking was. And at the end, each of these committees wrote defined 3 surveys, a nominal, a baseline, an underguide, which uses less time, and an overguide, which uses more time, and an associated report that describes all of those choices. And that process has been complete, and the reports have been submitted to the ROTAC. So to give you a flavor of what this looks like, this is one of the slides from the committee chair's presentation last week, and you can see what choices the committee is recommending for the galactic bulge time domain survey, which at a wild guess, I'm assuming most of this group care about. I think one of the most substantial differences in the current recommendation is that all of these options include a field at the galactic center, which of course is not optimized for microlensing, but it's enormously rich for a wide range of other topics. We're also considering doing slitless spectroscopy. We're doing the technical studies to see if we can actually guide in crowded fields. So it's not yet clear whether that will be feasible, but we very much hope so. Okay, so I personally feel that what we hoped to achieve with the community definition process really did happen. We wanted a larger section of the community to really feel that they owned a part of Roman, that Roman wasn't sort of for the use of a small number of teams with a small number of boutique science cases. And I think we achieved that in spades. There was a huge amount of input. And something I hadn't realized is that when you ask people to provide input on something like this, it spins off associated papers. People turn their white papers into journal papers that also appear on the archive. So you're generating more and more and more sort of buzz about Roman. The definitions now include, all three surveys now explicitly include some optimizations for astrophysics. So I mentioned the galactic center field, the high latitude wide area survey adds fill-in observations to extend the temporal baseline. The high latitude wide area survey added a much wider, shallower tier, all of which were driven by astrophysics and not cosmology or exoplanet demographic science cases. We also considered synergies with other facilities. You don't want to do stupid. It doesn't make sense, for example, to if you're in an area that overlaps with Rubin, to take observations in the blue, because you can get those from Rubin. So each of the surveys considered synergies with Rubin, considered synergies with Subaru. And the next step is for the Roman Observation Time Allocation Committee, and Eamon Cairns is one of the people on it, to synthesize all of these inputs into a recommendation for an overall mission observing plan. So the draft reports are available along with the committee presentation. So I saw some people taking photographs. You can get everything, the whole report, a lot more information if you follow that link. If you don't know how to follow that link, just go to roman.gsfc.nasa.gov and go to the community forum page. Okay, but we're doing more. One of the pieces of feedback that we got from our advisory committees is maybe we're leaving science on the table by only having those three core community surveys as surveys that are being defined now. So in 2021, we solicited comments on whether it would be scientifically valuable to pre-select the theme for a general astrophysics survey. And if it was, give us a ranked list of what those themes could be. The evaluation committee did find that there was a case for this, and they recommended that we proceed with a galactic plane survey. In very close second place was a deep field, and they recommended that at some point we have a community process to also define a deep field. So this is the process, the definition process for this survey is lagging the others because it got started later. Rachel Street, who I think might not be here, is one of the co-chairs of that definition committee. So feel free to talk to her if you'd like to know more about the potential in that survey. Okay, so that means that eventually the ROTAC will have a galactic plane too. Okay, Roman performance. This is an incredibly busy chart. I just couldn't think of something better on the short time scale to put here. What I wanted to emphasize is that now that we've actually built most of the observatory, we're starting to update all of our performance estimates with as-built things. So one very important part of that is slew and settle times. And we had been carrying a conservative value for the amount of, for how hard we could run our reaction wheels. And that was driven by an uncertain set of thermal constraints. Now that we've built the observatory, we know that we actually can run the reaction wheels at full tilt. We know what the mass of the observatory is. The mass is light. What that means is that Roman can accelerate and decelerate much faster than we were assuming before. And that means that the kind of observation where you do lots of little slews and short exposure times are particularly enhanced by this improvement, which of course describes the galactic bulge time domain survey. And I think it also helps explain why the optimal way to use Roman really is to tile or dither across the sky, because our observatory is optimized to do those kinds of observations well. We're also in the process of providing updated information about the detectors, the filters, the PRISM and GRISM and the overall optical model, and the analysis of the TVAC data on that is underway. So I'll keep going. Okay, Roman and external synergies. This is extremely important, and this is not a complete list. But I think it's very important to emphasize that Roman doesn't operate in a vacuum, and that considering how we're going to use Roman observations with the observations from other observatories is a massive multiplier for Roman science. And of course, the converse is true as well. Roman observations will be a multiplier for the science return from other observatories, two-way street. So I'm listing some of the three areas. The Vera Rubin Observatory is sort of our ground-based counterpart. They provide observations into the blue. We can help with deblending. They're a pathfinder for sort of a community approach to defining surveys. They're a pathfinder for doing astronomy in a science platform. I'm very happy that they get to experience this before we do, so we can learn from their experiences. We have a really nice program with the Subaru telescope, where there's 100 nights for the Roman community to use as part of an agreement with JAXA. And the way to think about this program isn't we are given 100 nights. It's to spur collaboration between the US and the Japanese communities to find a few large programs that can really enhance the leverage a chunk of observations to enhance Roman science. There's a white paper call on that open right now with a deadline of February 28th. And there's a community workshop, will be a community workshop later this spring, where we will announce the themes for the Subaru observations. And then finally, Euclid is our sibling in space, another near-infrared observatory in L2. We've had incredibly productive discussions with the Euclid technical team that have resulted in improvements and sort of adding robustness on Roman. And there's some very interesting precursor observations of the Roman galactic bulge survey field that will have substantial science return for Euclid itself and for Euclid and Roman combined that you hear about later in this meeting. How am I doing on time? 5. Perfect. Okay, we've got a plan for data flow. It's really simple. It's just all these boxes, and that is just how it works. The reason I'm showing this is to emphasize that our system is almost all cloud-based. So we download the data straight onto a NASA cloud. It's all in AWS East. The Science Operations Center at the Space Telescope Science Institute are responsible for the exposure level pipeline, so taking everything from raw data to calibrated pixels. At that point, it splits, and the Science Operations Center do the high-level imaging as part of the pipeline, and the Science Support Center do spectroscopy and microlensing. The reason I'm showing all of this is sometimes people say, oh, isn't it really stupid to have two science centers? Well, it really isn't, because we're all effectively operating in the same place. You, the user, can download the data in the traditional way, or you can use the Roman Research Nexus, which is a science platform, and be dropped straight into a Roman analysis environment and do your analysis that way. We have had some community workshops. We're getting really good feedback on the function and use of the Nexus, and you can expect to see more workshops advertised over the next year. Okay, working together with the science community, this is important. We really continuing to try and focus on community building and collaboration. I think it's really essential for a survey mission. There are two key paths to this. We have a set of technical working groups that are where people with different science interests can come together on topics of common interest. These are typically in areas that are important for the project. We need input from the science community on the optimal way to handle calibrations, on how to implement the operational pipelines, on the simulations that we're using to test everything, and so on. We also have just started a science collaboration that Jessica Liu is one of the co-spokespeople, and this is a way to engage with each other scientifically, independently of whether or not you have been selected by NASA for an award. And we think that this is also going to be a way to really help people find each other and maximize the science. So I'll skip this. If you want to join the technical working groups, you just sign up on the Roman forum. There's a QR code there. Feel free to do this, or if you want to join the science collaboration, these are distinct because we're not assuming that everybody wants to be part of the science collaboration, although I can't imagine why you wouldn't. We're having a Roman Science Conference at the Institute this July. Please mark that down in your calendars. It's going to be great. We have proposal opportunities, which I'm going to fly past, except to say Roman data have no proprietary period, and our processing is entirely data-driven. So the community has access to the data at the same time as anybody in the science centers, anyone in the project. Our proposal, roughly every second proposal cycle, will allow you to propose for observations. But the expectation is that the majority of Roman proposals are going to be to develop analyses on the data from the already defined surveys. But don't let that stop you thinking about additional Roman observations. But it is a flag to say you're likely to be much more successful if you need funding and you're in the US to just apply for analysis. If you're anywhere in the world and you want to propose a Roman survey, you are free to do so. And this is a summary that I'm not going to go through, and I think I will just stop here with a summary of how you can get and stay involved. Thank you.
So I'm curious, so you mentioned this data rate of 4.8 petabytes, right? And the cloud computing part. How is that done in practice?
So actually, I'm down. The question was, how do we manage the cloud computing in practice? The contract that we've negotiated with Amazon provides a fairly large area that does not have egress costs. So our expectation is that we can maintain a cloud-based data archive where people can download freely without incurring cost for them or us. The implementation of an analysis environment takes several different paths. So we actually have multiple different ways that people have set up their compute environment in AWS. So there are a couple of implementations on different NASA-provided entry points. The Roman Research Nexus is implemented in AWS on a different contract, but it all is working reasonably well, seamlessly at the everyone gets together level. I'm not sure if I answered the question.
Yeah.
And concerning the flexibility of the survey, so suppose that we, after the first run of the microlensing or the galactic large time domain survey, we realize that something is not going well, and so we are not going to meet our size requirements for microlensing yield. Are there any possibility to for example, to change the summit and to restore the original design and avoid the galactic center field, for example, if we want to give priority to microlensing?
The answer is yes. We're likely to have a review of observations something like about 6 to 9 months into the mission. I feel quite strongly would clearly be insane to learn something about the observatory or the sky and ignore it and just pig-headedly proceed with the observations we'd planned. We have not yet figured out what the mechanism is for how we get advice on what changes people are recommending and how we make decisions on that. So for example, it depends how the microlensing requirements are not being met. You might choose to either waive the requirements and still change the survey in some way because you realized another very pressing or exciting science goal. I mean, I think we will try and be flexible.